Welcome back, Earth Science. You can probably tell from behind me that it's a different time of day. I like to wait until it's dark out to talk about stars. So we're talking about the trails that stars make across the sky and how we can tell what direction we're looking at based on those star trails. Now, we know we have to look in the southern sky to see the sun, and that the sun rises generally east, arcs across the southern sky till it hits, high noon, and then it sets generally west. Stars are a little bit different because stars, we can look in the southern sky, yes, and the stars will take the same path as the sun. But we can also just turn our bodies and look east, or turn our bodies and look west. We can actually turn our bodies and look north and see parts of space. So unlike the sun, where we have to look in the southern sky, we can look at any direction and then see stars. So let's take a look at how we can capture this from our notes. So in your notes on page number, make sure I got this right. Page number 6, please. On page 6, it says the apparent daily motion of stars. And this diagram here, there's a bit going on. So you have the celestial dome, but the way the author presented it, like north is here, south is over here, east is west. So this is kind of tilted at a diagonal, which is fine, but all this is new to you, so I don't want to confuse you. So to make it a little easier, let's take a look down below, because I think this helps straighten it out. So if you're looking east, all stars are going to appear to be what I call rising. They're going as the period of a few hours goes by, you're going to see them go from a location here to a location here. So they're going to be getting higher in the sky. If you're looking west, the stars are going to appear to be setting. So over a period of a few hours, it'll go from here to here, and eventually it'll go below the horizon, and you'll no longer be able to see it anymore because it did in fact set. If we are to look south, I want to jump to here. The stars will make a arch across the sky, the same as what the sun does. So they'll rise, they'll hit a high point. We don't call it noon because they're stars, but it'll reach some high point in the sky, and then it will set. And then if we're looking north, the stars will appear to go around in circles, and they're going to go around the star Polaris, because Polaris is above our axis of rotation, which we covered when we covered latitude and longitude. So it's very important that you have this written down, because what the Regents will try to do, and what I will try to do on quizzes, is just give you a star direction. In other words, just give you something like this, a star with some arrows, and say, what direction is the observer facing, or what direction are you facing? Just based on that tiny bit of information. So there's only 4 things to sort of memorize here, but it's important that you memorize them, quickly. So let's take us a little bit further here. So it says the apparent daily motions of celestial objects like stars changes when the observer's latitude on Earth changes. So as you might expect, just based on what we've seen with the sun, when we get to the North Pole, so 90 degrees north is the North Pole. When we get there, no stars appear to rise or set. Instead, all the stars just go around in circles. But if we stop and think about it for a second, it makes sense, because if we look north, all the stars go around in circles around Polaris. So when you're at the North Pole, you're as far north as you could possibly go, and the stars are just going to go around you in circles. The sun does the same thing, by the way. You're at the top of the Earth. At the equator, all stars rise and set. Oops, I'm sorry. Lost it here. Just went to the bottom of the page. So at the equator, all stars rise and set. So there aren't any stars going around in circles. You're at the spinning part of the Earth, like as most spinny as you can get. You're at the equator. So all the stars are going to rise and set. They're all going to take these vertical paths across the sky, which we covered in a previous video. That's also what the sun does. So when you're at the equator, everything goes right up and over. At the poles, everything goes around in circles. And this should look somewhat familiar to you. Oh, I did it again. Here, sorry guys. Here, Mayville. It's 43 degrees north, we're like 42.5, but 42 in 30 minutes. But let's just stick with that. Between 42 and 43. Some stars circle, some arc, some rise and set. So when you're drawing this, all of these celestial domes, make sure you're putting your directions on there, because with star paths, it's very important that we have our directions, because that's really what defines them. So here you can see in the northern skies, the stars are going around a circle. In the southern sky, they're arcing across the sky. If we look east, they're all going to appear to be rising. And if you look west, they're all going to appear to be setting. Give you a moment to get this information down. And when you're ready, if you need more time, just pause the video. And when you're ready, come on back. Okay, the last note on this topic is the apparent daily motion of the Big Dipper. Now, the Big Dipper is a circumpolar constellation. So from that word circumpolar, it's going to go around, it's really going to go around Polaris. So if you remember back to latitude and longitude, we used the front cup of the Big Dipper to find Polaris. So you use these two stars in the front, and then you go about 5 times that length, and you'll find Polaris in the night sky, which I hope some of you have been able to do, just even on your own if you happen to be outside. And with all this darkness coming, there'll be ample opportunity to be outside and see stars. A good chance to actually find Polaris. You'll see it's not the brightest star in the sky, but once you know its location relative to the Big Dipper, it's pretty easy to find. Now, the Big Dipper throughout the year goes around Polaris. And so, like in this case here, the cup is off to the left. In this case here, it's to the bottom, like it's between Polaris and the horizon. And then this position here, it's off to the right of it. I think this is where it is right now, but let me see from my notes down below. I found it the other night, and I'm pretty sure it was there, but we'll see. So the location of the observer, the date's mid-October, New York State. So at 9 o'clock p.m., it's at location 1. 3 o'clock a.m., it's at 2. 9 o'clock a.m., it's at 3. And 3 o'clock p.m. it's at 4. So I was wrong. I did not see it from that location because it would be 3 o'clock p.m. That's not where I saw it from. So my memory has failed me on this one. But as the day goes on, the constellation goes around and circles around Polaris. And it also changes its location at different times throughout the year. That's why I said date mid-October. I'm going to try to spare you some of those details. I don't want to explode your guys' brains. Time-lapse photo of a star. We saw these guys when we were talking about latitude, longitude. So the time-lapse photos of a North Star, they're going to go around in circles, make those really pretty rings that we saw, as long as you're looking north. So it says time exposure, 4 hours. The angular distance of the star trails would be 60 degrees. So they'll give this to you sometimes. They'll say, all right, here's a star trail here. Here it is 4 hours later. How much did those star trails move? Well, it's 15 degrees per hour, so we're just going to take however many hours they gave us. In this case, it was 4. 4 times 15 is 60, and that's where we get the angular distance to the stars. This is pictures, time-lapse pictures, and you guys by now, even with this brief discussion, should be able to put what's north, what's west, what's east, what's south, and then fill it in. So go ahead and take a second and do that. Pause the video. Go ahead and fill this in. And then when you come back on, I'll tell you what the answers are, just to make sure that we're all on the same page. Okay, this one here, the big circles going around Polaris, this is going to be north. So A is north. B, the stars appear to be going horizontal, so I'm probably looking in the southern sky, so B is south. C, the stars appear to be setting. So this is going to be west, and in D, the stars appear to be rising. So that is going to be east. So we have north, south, west, east. We're going to leave it there because the solar system is not where we're at just yet. So with the star trails, we're going to pause there. But before, what I want you guys to do is to take this paper here. It's called Earth's Rotation. And I want you guys to complete this portion of it where all the words are. And then we'll go over it together in just one moment. Okay, I hope you've had a few moments to complete Earth's rotation. I'm going to run you through the answers. It says the Earth's axis is tilted blank compared to its orbit. That's going to be 23.5 degrees. That is our tilt of the Earth's axis, 23.5 degrees for that first bullet. The Earth makes one complete rotation every 24 hours. That's the second bullet. The Earth rotates from... Sorry about that, I had to sneeze. The Earth rotates from east to west. That's the third bullet. This means that we are rotating at a rate of 15 degrees per hour. That's the fourth bullet. Because the Earth is rotating, objects in the sky appear to move from east to west. Fifth bullet. This is called apparent motion. Okay, apparent is A-P-P-A-R-E-N-T, and then motion, M-O-T-I-O-N. The sun appears to rise in the east and set in the west. Remember, it's only due east and due west on an equinox, but still, generally east and generally west. At night, the stars appear to move across the sky from east to west, generally. This is what you see from New York State facing different directions over the course of several hours. These star trails, I'll try to put them right up to my camera here. East, they're rising. Oops. South, going across. West, they're setting. And north, they're going around in a circle around Polaris. Evidence supporting the idea that the Earth rotates includes the Coriolis effect and the Foucault pendulum. Now, if you're worried about spelling, they're both on your sheet in the bullets right below. The Coriolis effect states that objects are deflected to the right in the northern hemisphere and to the left in the southern hemisphere. And the Foucault pendulum swings back and forth while the Earth rotates. Okay, so Coriolis effect, deflected to the right in the northern hemisphere and the left in the southern hemisphere. The Foucault pendulum swings back and forth while the Earth rotates. All daily changes this is the big print at the bottom. All daily changes are a result of the Earth's rotation. Good. You guys can turn this into the box. The last thing you have to do for today, I know it's been a lot of screen time, I appreciate it. We actually did cover quite a bit of ground. The last thing I want you guys to do is to watch a video by a teacher named Michael Sammartino. He's very good. And this video is on rotation and revolution.